Hello, everyone. My name is Michael Guerin, and I will be the host of today's webcast, where we will be discussing what kind of ingredients we would need to get another cold winter in the US and what that winter might look like in a warming climate. Here with me today is Dr. Paul Roundy, a professor at the University of Albany. Dr. Roundy studies waves of the tropical atmosphere and ocean and how these waves interact with one another and with atmospheric moist deep convection to modulate global weather and climate. He also has a couple of areas of emphasis, which include analysis of observations to study modulation of tropical cyclogenesis and ENSO by convectively coupled waves and intraseasonal oscillations. That was a bit of a mouthful, but without further ado, Dr. Roundy, our first question, what kind of signals or combination of signals, like ENSO, MJO, NAO, etc., well, we need to get a real winter again, like something like 2013, 2014, where it was super cold for a good portion of the winter. Um, what kind of signals would we need to see to get something like that here in the US again?
Yeah, so I have some context in the slides. Maybe I should show my slides now.
Sure, yeah.
Yeah. So let's see, share screen. I think I'll just share my whole desktop and then I can hit play on the slides.
Yeah, I can see the slides.
Yeah. So um, I've been watching uh, the large scale weather patterns over North America and across the world, especially in association with tropical convection and how tropical convection interacts with the global atmosphere since the late 1990s. Um, and so I'm going to present some slides showing Januaries from each year since 1997. And so we can get some picture of just how conditions have varied since that time, and so we can look at the trends in the context of the year-to-year variability, and then discuss how individual year outcomes evolve, where cold air originates from, and so forth. And I guess this is an almond blossom from my garden. Uh, I am growing almond trees in upstate New York. And in past decades, you might have expected the buds to survive the winter in maybe 2 out of 5 years. And now you may maybe expect them to survive the winter 3 out of 5 years. To survive the winter, the buds can't experience low temperatures for longer than a few hours, colder than 15 below Fahrenheit. And so it's a good metric of how things are changing, and also to kind of set the context for what gives us a truly cold situation. I mean, here in east of Albany, New York, 15 below isn't a common occurrence. Like it might be a common occurrence in the Dakotas and Minnesota. But we occasionally get that cold. Last year, not this previous winter, but the winter before, we were 15 below. It doesn't take an abnormally cold winter to make an abnormally cold night. And that's all you need to destroy these is an abnormally cold night. And so just for an example, in 2015, 2016, that strong El Nino winter, it was the warmest winter on record until moving later in the season. And around the end of February in 2016, we had a cold outbreak and it was 16 below at my house. And all of our peach and almond buds died. And so there's a different context between a short-term cold event and an extensive cold event, which I think
Right.
you were referring to here. But in addition to the almonds, I grow these. in my front yard. These are called the Musa Basjoo hardy banana, which can survive the winters here under 3 or 4 feet of wood chips. And I just uncovered them last week, and they're starting to grow again. But the last 2 nights we've had frost. So if we want to get the context for how it gets cold in the eastern United States, we need to think about how cold emerges in the first place. And cold air, of course, is a consequence of a temperature balance. That is, temperature balance that favors cold, which means, for example, high outgoing long-wave radiation over snow, which is a good radiator, high albedo or darkness, which both imply less energy coming in, and weak winds, that is not much mixing of intrusion of warm air into the cold air mass. Once you have the cold, you can move it around, and that's of course, the advection of the cold air. And let's see, there we go. It's typical that on a seasonal time scale, we can get patterns that favor cold by when low frequency background conditions favor ridging from the Bering Sea region east to Western Canada, which can then allow for southward transport east of the Rockies of cold air. And the low frequency tropical background conditions will include things like the Indian Ocean dipole, the El Nino Southern Oscillation. But it takes more than just a favorable background convective condition in the tropics to create a cold outcome in, say, in the eastern United States, because it depends on the shape of the tropical background convection and so the geographical distribution of tropical convection, but also the mid-latitude waveguide across which the response to the convection propagates. So I study a lot of ENSO and the Madden-Julian oscillation as particular precursors for cold or warm outcomes. But a given structure in the extratropical circulation that results from the forcing in the tropics isn't unique, because the wave train response to the convective forcing in the tropics depends on the waveguide in the extratropics. So it depends on well, how the polar vortex is organized. It depends on where the potential vorticity gradients align and how strong they are, because those present the restoring force for the Rossby wave response to the tropical convection. And I use composites of the average condition in the global circulation associated with tropical forcing, with the understanding that an individual event will vary based on the extratropical waveguide across which the response to the MJO and the El Nino signals are propagating. Another way you can get cold is what I'll call, extensive cold over weeks at a time, is what I'll call serendipitous sequential subseasonal forcing. The timing of the MJO with regard to its seasonal cycle of response patterns can favor perpetuation of cold for longer than the MJO alone would have done. For example, you might expect a 1 to 3 weeks of cold signal associated with an MJO event if everything in the extratropics stayed the same. But because the wave train response patterns evolve with the seasonal cycle, you can expect that the phase that favors cold in the eastern United States changes with the seasonal cycle. I'll give an example in this slide here. This is phase 5. in the first week of January. Or this is day 10, roughly first week into the second week of January. And phase 5 is typically associated with warmth for most people for the winter months, but this is what it looks like in early January. And then you move forward, and now it's warm into March. So I chose this just as an illustration of how the seasonal response, changing response to the MJO evolves, and that you can get cold and warm outcomes from different phases. But if you happen to have aligned with the right time in the seasonal cycle and the right starting phase, and you go across a phase circuit, you might start in a phase that favors cold and evolve into a phase that favors cold. So this is how one way that you can get a longer than subseasonal timescale response from a subseasonal signal. Cold in the middle latitudes can also evolve from mid-latitude dynamics, synoptic weather noise, independent of any kind of mid-latitude or tropical forcing or low-frequency forcing. For example, a storm event can lead to Rossby wave propagation vertically into the stratosphere and displace the polar vortex, and then favor front formation where the vortex aligns with the Arctic to mid-latitude temperature transition, and you get baroclinic instability that winds up and enhances the equatorward flow of cold air. Of course, especially early in the cool season, typhoon front interactions over the Western Pacific, releasing latent heat, can generate wave train responses that generate blocking. And then once that blocking is in place, if it's not displaced by some larger scale feature, if you keep feeding it with wave energy, the waves keep breaking in the same place, and you can get perpetuation of longer timescale features. For example, driving an Alaska ridge that just keeps renewing over time. And so comments or questions so far?
No, I think that makes sense. Everything you said, it's I thought it was a lot of people I think forget. I just kind of want to highlight it. With the MJO you mentioned, where you can get the same kind of setup in the tropics, but you get a different result sometimes because of what's going on in the extra tropics.
Yeah.
And I thought that that's
Sometimes,
yeah. Go ahead. No, sorry.
yeah. Sometimes that's a result of the waveguide
hmm
changing, and so the waves break in a different place. And other times it's a result of another mode, some other quasi-comet semi-independent signal. It can even be tropical forcing as well. You can have an equatorial Rossby wave that's producing convection in one place that's different from the MJO, and sometimes that overwhelms. Sometimes westward moving features dominate in the tropics over eastward moving ones. And if you're looking at the MJO and not the westward moving things, you're going to miss some of those features.
Right.
So I want to show what the last couple of decades of Januaries looked like. So this is just the cheap NCEP NCAR reanalysis for easy reference, looking at January monthly means, 2-meter temperature signals. And 1997, January, El Nino, typically there would be a big blocking ridge signal, which there was on average that season right here, which often on its own would create a warm signal across the northern tier of the United States and a cool cutoff cyclone signal in the south. And that did happen that year. It was robust in the season mean, but look at January. It's a cold Canadian prairies and intruding into the high plains of the eastern United States. And it was generated by subseasonal forcing. So now we're just going to move through the years. So 1997 is the pre-El Nino. And then this is 1998. This is the full El Nino January. But look, it's like I said, it's cold. It's cold in Canada instead of warm block. and we've got warm in the southeastern United States. Even on a monthly average, subseasonal variability can overwhelm the interannual variability of ENSO and give to you outcomes that are quite different. In this case, there was a pronounced cold air outbreak, actually similar to one that happened this year. In January, was it? This year we had a northwestern Canada, and it broke out, came down into the western United States, and then spilled over into the east and just bled across and mixed out. My wife, this last January, was in Nebraska driving, and it was like 15, 20 below, and it was just a whiteout blowing. There was not much snow falling, but lots of snow blowing. And 1999, La Nina emerges. La Nina again, 2000, kind of go neutral. In this case, there's Western North American warmth, but it's shifted to the east far enough that the cold is introduced like a big El Nino event would put it into the south. 2002, 2003, this is El Nino, Central Pacific pattern. 2004, 5, 6, warm year, 7, 8, 9, cold Eastern United States, 10, cold Eastern United States, a little farther south. 2011, also cold, La Nina situation. Another La Nina situation, but 2012 is warm. La Nina typically would favor a trough or a ridge here and a trough here, but you're getting a subseasonally forced pattern that's overwhelming the monthly mean. 2013, 2014, this El Nino is trying to grow that year. So there's Central Pacific forcing, but you'll notice it's actually cold east of the date line over here. So cold into the Eastern United States then. Cold in the far eastern, January 2015. This is moving into the big El Nino event of 2016, which has the classic Canadian block and southern troughing. 2017, 2018, 2019, 2020, 2021. We're beginning the multi-year La Nina event, and it's warm in Canada. Now cold La Nina, warm La Nina. El Nino, the big El Nino event. And here's that cold outbreak I mentioned. It began in northwestern Canada, bled into the western United States, and then east. In the monthly mean, it was east of the Rockies. This is this recent winter. And we did have a pretty hefty cold outbreak, more than one into the western United States, and then some bleeding into the east, especially in the plains. Northeast had a mild winter, and my peach buds and almond buds survived as a consequence. Here's the trend. This is the 2000 to 2024 minus 1976 to 99. So we're basically looking at an average, give or take, between 2010 and 1990. So watching how much conditions have warmed. And I mean, you're talking 1 to 3C across Canada, warming across the northern plains, just a little bit of warming, less than a degree across up the east coast here. But comparing this with the year-to-year variability, you can barely even see the climate change trend in here, because the internal variability is so much larger. So, I mean, obviously, this signal is very real, and it's having an impact in our seasonal outcomes. It's changing this is January again, but if you move into the spring, the warming is shifting the frost-free time earlier in the season. But last year, what happened in May in the northeastern United States? May 23rd, it was 26 degrees at my orchard, and all the buds die. My grapes die all the way back to the vine. Luckily, they're mature enough. They grow out and they ended up regrowing and they bloomed again. And I got fruit anyway. So, how much time do we have? Just so I can kind of gauge.
We have about another 15, 20 minutes or so.
Okay. So I want to show some of the tropical background states between some of the cold and warm years. I mean, 2014 was a cold event. And this is NOAA interpolated outgoing long-wave radiation. So the idea is to show across the tropics, where is it raining and where is it dry? And we're looking in 2014, the Central Pacific has suppressed convection. I should have switched this color bar. Active convection is situated in the West Central Pacific, which is a nice forcing position to create ridging over here, and then cold coming into the eastern United States. This benchmark somewhere between 160 degrees east and 210. Dateline convection is often a great place to force a cold outcome in the eastern United States. Here is the height pattern associated with that event. So you can kind of see the PNA pattern and the cold trough in central Canada. 2010, it's quite different. Go back to the convection is West Central Pacific, and come to 2010, the convection is Central Pacific here. So I did swapped in this case. So this is where it's this is where there's active convection. So active convection at the dateline. And there is the response pattern. It's shifted east of the previous one. So now the block extends from Northwest Canada east to Greenland. And this helped favor the cold outcome that year. Of course, again, don't attribute a monthly mean just to the ENSO condition, because subseasonal patterns will also be contributing. 2011. In this case, there is suppressed convection in that target region. There is active convection across here and here to the south over Australia and extending over the southwestern Pacific. Tropical cyclones that organize in this area over the South Pacific can induce a ridge response up here, which can look a lot like what you would get if you had mean state convection centered on the dateline. And here is the pattern in 2011, where there's South Pacific forcing and a Rossby wave train response. Here is January 2022, and we have suppressed convection with our La Nina event. And here is January 2023. Principal difference, not something people normally look for. Look at where the center of the suppressed convection is in a meridional sense.
Yeah, I was going to ask about that actually. I was like, does it matter how far north or south it is in reference to the equator?
So the response to heating, the release of latent heat in the tropics, can be roughly simulated by this simple model we call the Gill model, which is just really a shallow water model. If you put the heating right on the equator, you get a symmetric circulation response. So both hemispheres, in that case, if you have, in this case, suppressed convection, you would have north and south of the equator, you would have troughs. And then there would be ridges poleward of those troughs and then extending around. But when you move the heating off the equator, you end up getting an anti-symmetric response in both hemispheres with a trough in the north and a ridge to the south. And the result is kind of a rescaling of the Rossby wave response into the middle latitudes, and you get a different outcome. And virtually no one looks at this, to my knowledge. Everybody's interested. Is it El Nino? Is it La Nina? Is it Central Pacific? Is it this stuff matters? And the problem is that there's so many degrees of freedom in the system that it's just really easy to fit noise to a statistical model or to convince ourselves based on the patterns that we see. And we're really, like I said, fitting noise, and that gives no skill in the or low skill in the result. So you can account for this sort of thing by taking multiple EOFs of the ENSO signal as a predictor, and not just in a meridional average, but including the meridional structure. But of course, the more predictors you use, the more you're going to fit noise. And so it's catch-22. The natural system is complicated and I think very interesting. See, this is January 2023. Warm, looks like El Nino.
Mm-hmm.
Here is January 2022. I think I want to show just, I'll show a few of these. I use multiple predictors extracted from time extended EOFs of tropical convection in order to diagnose the generalized structure of the convective signal in the tropics. And this is just centered on a given date. So this is December 10th, and it's using the low frequency and the MJO and westward moving tropical convective signals. And it's suggesting a pattern that with a ridge in the eastern US and a trough. And we're looking at real time, no time lags here. So we just want to see how well it fits. And well, here is what was happening at the same time. There's a North Pacific ridge. It's in a little bit different phasing. Let's see here. Shifted to the west a little bit. And so the ridge, instead of being at the East Coast, ended up in Canada. You can consider many of these differences that will arise from the comparisons between the expected value and what actually occurred as being caused by the mid-latitude Rossby waveguide variations. That's the main factor, I think. 20th of December, this last winter, favoring Western Canadian ridge and Eastern US ridge. And this is what actually happened. 30th, now we're getting into a block in what actually verified. And now 10th, 9th of January, and we got this big miss. The ridges are there, but the whole PV gradient shifted to the north. And so wave breaking ended up dropping this upper level cyclone into the western United States. And this is when that cold outbreak occurred. And now this is the 19th and the 29th. This is the projected based on the tropical convection. And there now we're starting to get resync to the signal. And then projected again, a little shift to the east. Can't see it. The ridge is just a little bit farther north than what it projected. And finally, there is, on a general average over the Chicago to DC to Boston, this combined average approach to getting an outcome in the extratropical circulation has 60-40 chances of being right. And you know, I mean, one can figure out ways to include information about the mid-latitude waveguide in order to make it better, but then you just, start fitting noise as well and overfit. So finally, I want to reflect a little bit on the base state of the tropics and ENSO. What matters most on average to this December through February Chicago, DC to Boston mean temperature? So we're going to focus on the first two leading EOFs of sea surface temperature this time. And here they are. This I published in the Journal of Climate in 2015. We're looking at longitude, and this is surface temperature, skin temperature. Of course, in the oceans, this is sea surface temperature, but it's also land surface temperature where you see land. And the leading EOF is the blue curve. And get your bearings here. This is the date line right in here, and the East Pacific. Across this area, this is the Andes Mountains. And this is the East Pacific El Nino mode. And this green is the second EOF, which represents 1/5 of the variance of the first one, or 1/6. And it's the Central Pacific El Nino mode, which on its own is associated with warm in the Central Pacific or cold in the Central Pacific, because you can just flip these, and the opposite in the East Pacific. But it is the superposition between these two that dominates the location of the warmest anomalies. And so you can use the two of these like a clock, like a phase clock, like you would for the MJO, acknowledging that this one explains a lot less of the variance than this one does. Here are the two time series going back to late 1970s, going to the present. And you can see the big El Nino events. I switched the signs here so that the positive in the first one corresponds to El Nino. So you've got the spikes, the big El Nino spikes, 1982, 87, the early 90s, 1997, 98. This little period of the 2000s, 2002 to 2006, 2016, and the recent El Nino event. And the orange curve is the Central Pacific mode. It's typical in the big events that the Central Pacific mode comes up first, so you get Central Pacific warming. And then the East Pacific mode goes up while the Central Pacific mode goes down, which together maps an eastward moving interannual mode. But not all El Nino events behave that way. Sometimes the East Pacific goes up first and then the Central Pacific goes up, which implies a westward moving warm water anomaly. But now we want to consider what happens when we plot these two against each other and create a phase portrait and plot on it the temperature of Midwest East January in this case. PC1 is across the bottom, so this is the standard El Nino. So far to the left here is La Nina. Far to the right here is El Nino. Low to the bottom here is Central Pacific cold. Top is Central Pacific warm. And you may just see scatter right now. There's warm and cold everywhere, right? This is how you can get like subseasonal variability or changes in the mid-latitude waveguide that create the opposite of the expected outcomes. But there are twice as many cold signals at the top than there are at the bottom. So what it's telling you is that the Central Pacific warm mode is more likely to yield a cold eastern United States than the Central Pacific cold mode. And El Nino, going left to right, has a lot less association. This is now January to February mean, and it's clustering even more toward the top. And January to March starts to decluster and spread back. So just, going back again, January, February. This is January to February, and January, February, and March. So looking at the 3-month average, you still get clustering at the top end. So the general story is if you want to make a seasonal forecast, you would want to be basing it more on the Central Pacific mode than the East Pacific mode. The problem is that the Central Pacific modality evolves across an event. The 1997-1998 event began in 1997, March, April, Central Pacific, and moved east and became the strongest East Pacific event in history. Other events moved across toward the central and back. And so it depends how it evolved in terms of Central and East Pacific dominance depends on the weather events that evolve with El Nino. But when you're in a Central Pacific signal, it's harder to get East Pacific to emerge because the waves are breaking, the mid-latitude Rossby waves are breaking in a certain place, injecting troughs into the East Pacific upper troposphere, and then causing subsidence there, which is then reducing convection over the East Pacific, which is then enhancing the trade winds and enhancing the upwelling. So there is some resilience in the placement or existence of a Central Pacific dominated El Nino event, but it's like 60% confidence. So this is how you get cold in the eastern United States on a seasonal timescale by low frequency forcing. This Central Pacific mode is the favored pattern. And otherwise, it's based on what I call serendipitous combinations of subseasonal features that you can't predict a season in advance.
Right.
But that you can have some predictability during the season. And then there's the cold signals that emerge due to synoptic variability that is basically entirely unpredictable at a seasonal timescale, but can still project onto the seasonal mean. Good?
Yeah, yeah, that's a lot of information. Absolutely fascinating though, only have a couple minutes left, so I just want to kind of highlight, the point you made about, where the convection in the tropics is with relation to the dateline. Because when you say it, it just makes sense. Like, oh, of course, when it's north or south of a certain area, say the equator, it makes sense that it would have different impacts on northern and some southern hemisphere weather, though we don't really pay attention to the southern hemisphere as much. But um, it just makes sense when you say that. It's like, oh yeah, of course that happens. But I've never actually thought that before. I've never actually thought about like, oh, the north-south orientation of the convection actually matters for the impacts on northern hemisphere weather. So I just want to kind of highlight that again, just to really emphasize that, because that does sound like something, I won't speak for anyone else, but I personally have never even considered that as a factor. But when you say it, it's like, oh, of course, duh, I should be considering that.
There's a lot of degrees of freedom. In this last winter, we had an East Pacific El Nino event, but the maritime continent didn't cool nearly as much as it normally would have. And so normally the winds would have been stronger in response to El Nino, and there would have been less warm water stored up there by the previous year's La Nina events. So we had 3 La Nina events in a row. The maritime continent got really warm, and the El Nino forced winds were not enough to cool it. And so it rained over the maritime continent more than it would normally rain during a strong East Pacific El Nino event, which made the metrics of coupling, like the MEI index, appear weaker for this El Nino. But that also altered the North Pacific wave train. It still produced the block in Canada, but the North Pacific jet and westerlies was not as strong as normal because the North Pacific outcome depends on the superposition of the Rossby wave responses to the enhanced convection in the East Pacific and the suppressed convection at the dateline, at the maritime continent. So in this case, it's not just the north-south or or east-west of where the convection is. It matters where it's not raining as well. And it was raining where it would normally not have been raining. And so all these features matter to the outcomes. And so the world is a very complicated place. I, I thought Canada was going to be warm this winter, and it was on average. Um, but there's so many ways, different ways that this thing could have gone. I'll say one more thing on this point, that we were basing what we see as strong El Nino outcomes on 2 or 3 strong events without knowing what's the range of responses to 1,000 of those events,
Right.
including all the possible different configurations of the convection, maybe more over the maritime continent, more in the east, whatever, the different structures, north to south shifting, how strong the Indian Ocean dipole signal is at the same time. And it's just really easy to become overwhelmed with, I would
Right.
say you'd take 1,000 years in the same climate to get all of the possible ENSO configurations.
Yeah. Yeah, and I think a lot of people end up when it comes to ENSO, it's kind of like flipping a coin. You mentioned the three big ones. If I flip a coin 3 times and it's heads every time, well, it's like, oh well, that means every other instance has to be heads. That's what my data says. I am rolled heads or flipped heads 3 times. But when you've got something as complicated as the weather, um, you know, a 3 data points is I'm not gonna say meaningless, but in the grand scheme of things, it's kind of meaningless. 3 data points, especially if you need, you have all these different factors, and I'd wager a guess that all three of those Ninos you mentioned probably had completely different configurations in the extra tropics as well. So maybe not completely different, but enough of a
Yeah, there's
difference.
overlap, but um,
Yeah.
another related point is that many people are now trying to train their AI algorithms on
Hmm.
climate model data, because we have this problem of
Right.
not enough data from observations to converge material on all the different kinds of events that can occur. But you can create 1,000 years of climate data based on a climate model, and it'll do well as long as the signal in the climate model has similar enough dynamics to the real world. And we don't simulate convection well enough in these climate models yet.
Right.
So we're going to get some weird outcomes in some of these AI models based this way, trained this way.
Right. And uh unfortunately we're just about out of time, so we might have you back to talk more about absolutely fascinating discussion, and I'm sure we could spend hours here, but um, we can't spend hours here today. So, um, but Dr. Roundy, thank you for taking the time today to kind of go through this and go through what it takes to get a cold winter in the U.S. And we hope to have you back sometime at some point. The three of us will work out some kind of thing at some point, scheduling and whatnot to have you back. But we hope to have you back at some point to talk more about this and or any other future topics if you have an interest in talking about other topics as well. The AI, I know that's a big one that people are mentioning a lot more in these days, especially in regards to weather and weather, the climate, etc. Like to thank everyone for watching, and hope you have a great day.
Thanks for having me.